Okay, any other questions? Okay, let's look at, so in order to compute this, in order to play this game, another thing we need to do is to generate random expression. We're going to do a quick check to do that, what we looked at last week, and the gen type. Okay, so we're going to define functions to generate random expressions. So how do we do that? Well, we're going to define something like a random expression to be, well, it's going to be either a numeric expression or a binary operator. So I'm going to define two functions for those two cases. And I'm going to choose one of either a random numeric expression or a random binary expression.
What's a binary expression?
The data type has there's three different cases. It's the numeric one, and there's these two cases. I'm calling this the binary because they use a binary operator, add or multiply. So that'll be taken care of in a single definition. Let's make these local definitions. Yeah, why not? Okay, so what will a random number be? Well, for the sake of this game, let's suppose we want to keep the numbers fairly small. So let's take an element of the numbers from, let's say, let's define a range. Let's say the range of values is 4. So it's an element from minus range to range. So that's a number. But now we want to put that number inside. We want to make that into a. We want to. Okay, that's fine. We've got it. This defines a number in the range minus range to range, but we want to turn that into an expression. So one way to do that, the simplest way, is to use a do expression, and we want to say that the number that we randomly generate in that range is called n, and then we want to return num applied to n to get something in the expression data type. Okay.
We cannot just do a num applied to an element of -1.
So the type of element, we can do something similar. Yeah, I'll show you that. But just to be clear, the type of elements, it takes a list of things, and it doesn't produce a single thing. It produces a generator for things, and so we can't apply a function of this type to that unless we use what? Anybody remember? There was a trick to doing that. No, there was a function fman. But another thing we could do is we could map num over that list. So actually, this is a slightly shorter definition without anything too fancy. We create the numbers in the range, we map num over it, so we get a range of elements of the expression data type, and we simply choose one of those. So that's a neater way of defining that. Let me just define rbin. Rbin undefined. Okay. Okay, what about a random binary thing? Well, this one I'm going to use a do. What am I going to do? I want to choose whether I'm going to have an add or a mul. Okay, so I'm going to have one of those two cases. And I can do that by choosing an operator to be one of the elements of the list, mul, and add. Okay, so that looks a bit fancy, but these two things have the same type, so I can put them in a list, and once I put them in a list, I can choose one of them randomly and call that my operator. Then I'm going to randomly generate an expression. I'm going to randomly generate another expression. And I'm going to put them all together by returning the operator applied to the two arguments. Okay? Let's try it out. How do we try it out? Sample, a function called sample, or its friend sample prime. So now we can, let's check how I reload that, sample rexp. So I can sample that generator, And there you see it will randomly throw out some values. Some of them are a bit big and scary. Let's try a couple more times. Let's see if I can provoke this thing. All right, I'm trying a few times. Come on, come on. Oh, getting bigger. Getting bigger. I'm just hoping that I can get a monster. There he goes. Okay. You see what happened? Is it going to finish? I don't think so. It's not going to finish. So once a tree, you're randomly generating a tree, right? So once the base of the tree gets a bit wider, what's the chance of you terminating? What's the chance of you finishing at the next level? Well, it's a 50% chance that you'll get a number for each of the leaves in the tree, right? So once the tree starts getting bigger, the chances of you actually terminating get smaller. So once you kind of hit a certain threshold, chances are you're just going to build an infinite tree. Okay? Haskell is very happy to build infinite things, and it will actually show them to you as it builds them. And they're also fine. There's nothing wrong with them if you only use a finite part of them. Okay? If you want to eval them, then you'd be in trouble. But if you wanted to just look at bits of them, that might be perfectly okay. But clearly, in this example, it's not going to be okay. Now, one way to fix this would be to use the function frequency to control the relative frequency of the two cases. That actually turns out to be not a very good way to fix this. We don't get a nice distribution of expressions. What I'm going to do instead is I'm going to add a size parameter to this thing. I'm going to add a size, and I'm going to use this size. So Rx is going to be something which takes an int size parameter and computes a generator for expressions. So I'm going to pass in a size parameter, and I'm going to use that to control the frequency. So I'm going to do a frequency with a frequency, relative frequency of 1. I'm going to generate a number, and with a frequency of s, I'm going to generate an R-bin. But actually what I'm going to do is actually going to pass s in as a parameter to this guy. So what will the parameter do? Well, the important thing about the parameter is that I'm going to make sure that at each recursive call, I'm going to shrink the parameter. And I'm going to shrink it by halving it, roughly. So that means pretty quickly, this will get down to 0, and I'm guaranteed to pick a none. Okay? Because once the frequency becomes 0, then we have no problems. So what I'm going to do is I'm going to pass in s div 2, integer division here. So I'm going to divide s by 2. And I'm not going to so to avoid the cut and paste to do it the same down here, I'm going to just define it up here. That s prime equals that thing I just typed. What was that? S div 2. And that will be s prime now. Okay, so you see what I've done. I've added a parameter, and I've passed the parameter into this recursive generator. And I've made sure that each time you call it, the parameter halves. So pretty soon, you'll get to 0, in which case you're guaranteed that you'll only use this one. So let's try that out, see if we can do it. Let's retry the previous example. Now we can't do sample Rx. We need to pass a size parameter. So let's try size 4. And then we see we're going to get some nice sized, 4 seems to be quite a nice size actually for this problem. Okay, any questions? Okay, so we might also want to use these random generators in QuickCheck. Okay, so if you remember, we can make QuickCheck able to use, to generate random test data for expressions by making expressions a member of the arbitrary class. So if we say that we've got a new instance of arbitrary, named expression, where the arbitrary function equals what? Well, we could use our expression with some chosen value for s. But if we choose the value of s, we're bounding the size of the expressions that QuickCheck uses. What QuickCheck likes to do, it likes to start off with small examples and let them grow. Okay? So this doesn't really fit that well with QuickCheck if we provide a fixed parameter. It turns out that QuickCheck contains a function called sized. And sized is a way of taking one of these sized parameterized generators, like this guy up here, and it will turn it into a generator. And how will it do that? Well, what it will do is it will use its own internal random numbers and feed them in as a parameter in order to generate the random values. The magic of that is that when QuickCheck generates numbers, random numbers for testing, they're not very random, they start off small and they get bigger. So what QuickCheck will do is initially it will feed in small numbers here to get generators of small things. And then as time goes on, as you do more and more tests, it will feed in bigger and bigger numbers to create bigger and bigger test cases. So we can use the function sized from the QuickCheck library to define, we want the sized version of this rexp. And so now we can do sample. We can sample arbitrary at type generator for expressions, and then we'll generate random expressions. And the first ones, the early cases it generates will be small, and then they will start growing rather quickly. And that's the typical QuickCheck way of generating things.